Good evening. For this program, out to the two giants, Jupiter and Saturn. But first, some exciting news from Mars. The Phoenix probe has landed there and is showing signs of working very well indeed. Latest news, here is Chris Clinton.
This is our first view of the Arctic Circle on Mars, provided by Phoenix just after landing. With desolate plains stretching into the distance, it's not everyone's idea of a holiday destination, but the scientists are here for one reason and one reason only: ice. Measurements from orbiting spacecraft have indicated the presence of substantial amounts of water ice underground. Phoenix's task is to dig beneath the surface and investigate the role that ice might play in making Mars a home for life. Having hit the atmosphere at 13,000 miles per hour, Phoenix's heat shield reached temperatures of more than 1,000 degrees centigrade before the parachute was opened. This remarkable image, captured by Mars Reconnaissance Orbiter, caught a moment of the probe's descent. In its final stages, Phoenix completed the first powered landing on the surface for more than 30 years.
Touchdown signal detected. Landed it.
The first images revealed a scientific jackpot, features called polygons. These are caused, on Earth at least, by the melting and refreezing of ice. Is the same cause to blame on Mars? Phoenix will tell us. Phoenix's mission will almost certainly end as the spacecraft is engulfed by the long Arctic nights. Until then, Phoenix has plenty of work to do.
And now for our main theme. New missions to Jupiter and Saturn are being planned, both in Europe and by the Americans. But both planets are fascinating. So which should we go to first, Jupiter or Saturn? With me, two distinguished professors who are involved in all these missions, Professor Michele Dougherty and John Zarnecki. Well, John, Cassini is still orbiting Saturn. But why do you particularly want to go to Saturn first rather than Jupiter?
Well, how did you guess, Patrick? Having spent, 15 years of my professional life working on Huygens and delivering an instrument to Titan, I have to vote for going back to Saturn and in particular going back to Titan. I mean, it really has almost everything that one would want as a planetary scientist.
What, for example?
It's got methane seas, it's got rivers, it's got mountains, it's got dunes, it's got a wonderfully complex atmosphere. We see complex chemical reactions producing complex organic molecules. It's got all of the building blocks that we need for life.
I'm even more interested in Enceladus, this tiny satellite with its fountains.
Well, of course, it's one of the great surprises of the Cassini-Huygens mission. If you look at all of the predictions from 10 years or so ago, I don't think anybody would have predicted that Enceladus would turn out to be as exciting, as active as we now know it is. I mean, it is absolutely a complete surprise.
But of course, you don't quite agree with that, do you, Michele? You'd rather go to Jupiter first.
Well, I'm torn, Patrick. I must confess I'm sitting on the fence. I'm involved in science definition teams looking at both. But since John is voting for Saturn, I will vote for Jupiter today.
Why?
We want to focus on two of the moons of Jupiter. We want to put a spacecraft into orbit around Europa. We know there's an icy surface at Europa. We're almost certain there's an ocean beneath that icy surface. And we want to try and understand how deep the ocean is and whether there might be life at Europa. We also want to try and understand Ganymede, because Ganymede is the only moon in the solar system that has an internal magnetic field. And so we want to try and understand how that was formed.
At the moment, of course, Saturn is well placed, and any small telescope will show the ring system well. Jupiter, not so good from here, I'm afraid, but nevertheless, you can still see the belts, moons, and the great red spot. Well, what about Jupiter? What do you particularly want to find out, Michele, about the planet itself?
I think we want to try and understand how the magnetic field of Jupiter interacts with the plasma environment around it. And to be able to do that, we need a spacecraft to orbit around it, because we want to try and understand if the environment of Jupiter has an effect on Europa and on Ganymede as well. And so we really want to look at a whole lot of different sets of problems with as many spacecraft as we can.
But talking about the environment, of course, it's a much harsher environment, isn't it? If we're talking about spacecraft. I mean, for example, the Europa orbiter that's being studied at the moment, I think its lifetime, once it arrives there, is perhaps only a couple of months because of the radiation. Isn't that correct?
That's right. It's going to be really difficult to have both the spacecraft and the instruments on board to be able to survive the really harsh environment.
And what about Io, the volcanic satellite?
Io we will fly by once or twice, I think, but we will only use it to get us into the correct orbit around Europa. The focus is really going to be on Europa itself.
But Europa is a big thing. It's nearly 2,000 miles across. We think there's an underground ocean inside Europa, below the ice crust, but how do we know? We can't see it.
Well, you know, we keep talking about this subsurface ocean, and
Is
we've
it
been
really
talking
there?
about it for so long. But
Yes.
what is that crucial observation that we're going to make to absolutely tie it down? Can we make one? What's it
I
going
think
to be?
that the hope is we will be able to get an understanding of what the depth of the ocean is, because once we know how deep it is, we'll then know whether it's in touch with the silicate
But
mantle.
how will we know it's there? I mean, it's still
We
only
will-
inferred.
Can we prove it? Can we prove the ocean there?
Yes, if we have a radar instrument on board, if
To
we
see
have...
through the ice crust.
Yes, so really to be able to tell how deep the ice crust is. We'll probably try and have a laser altimeter on board as well, because that will also help us sound how deep it is. A magnetometer will allow us to resolve what the conductivity of the ocean is.
And what about if we make very sensitive gravity field measurements? Will that be good enough also to tell us anything about the interior?
I think if we have a combination of gravity, radar and magnetometry, then that will probably allow us to resolve that.
I mean, some people won't believe it until we actually land and deploy. I mean, people have talked about melting probes. One of the problems we have, isn't it, with Europa, is slowing down to land. You see, with Titan, you've got the atmosphere,
Yes,
which
indeed.
helps you enormously.
That's right.
On Europa, the orbital dynamics and so on are such that you have to carry a lot of
Mass to...
yes, in the form of a motor,
Yeah,
or a
that's right.
retro rocket to
And
slow
of course,
you down.
Europa's own atmosphere is absolutely negligible.
It's negligible, so
It is.
it helps you nothing in slowing down.
One
So it's a
of-
very tough
One of the
environment.
ideas that people have is maybe to have a few penetrators which can essentially be dropped off from the spacecraft and land on different places on the surface. It's a very icy surface, though, and so how can we ensure that the penetrators are going to survive? So actually, at the moment, there's some tests being done on penetrators in the UK. They're being fired at blocks of concrete just to see if they survive.
If there's a sea there, a sunless sea, what would it be like? What would the composition be? Ordinary water?
From the observations we got from Galileo, we think it's a salty ocean, but to be able to resolve how deep it is, you need to make a guess at what the actual conductivity is. And so we think it could be up to 10 kilometres in depth and maybe as salty as the ocean on Earth.
Well, people are going to say, of course, any chance of life?
Probably not life as we know it on Earth, but to be able to generate life, you need water and you need organics. And I think some of the observations from the Galileo imaging spectrometer showed that there were organics on the surface of Europa. So we've got at least two things that you need to be able to generate life.
And a source of heat.
Yes, yes.
But of course, what about Callisto? A very different kind of place.
Callisto is very different in that it's undifferentiated. There isn't a core and lots of different layers in the interior, but the surface looks very similar to what you see at Europa. But then the surface of Ganymede is icy as well.
And what about Ganymede itself? The biggest satellite in the solar system, bigger than Mercury, bigger than Titan, but a negligible atmosphere.
That's right, but the really interesting thing about Ganymede is it has an internal magnetic field. And that's really strange because you only expect a field to be generated in the interior if the body is large and it's still giving off heat. Ganymede, although it's a large satellite, it's small compared to all the different planets, and so something is still heating the interior.
And doesn't that also
Ganymede.
perhaps support the idea that maybe there's liquid, a subsurface ocean as well?
In Ganymede, too.
Yes,
Yes.
not that. I don't
Yes.
think there's the same amount of observational evidence, perhaps, but the models based on
But that's right.
the
They
magnetic
think there's
field and so on.
there's a combination. There's a small icy ocean.
Ganymede itself, it's a fairly big thing, but Enceladus in Saturn's system is not. It's a tiny thing, and yet there are fountains there. How do you work that out?
I can't. I mean, if you look at all of the predictions that were made before Cassini-Huygens arrived, I think none of them talked about anything like this, because the fundamental problem is the source of energy driving the geysers that we see.
Well, Cassini has flown through the fountains, hasn't it?
It has, and those results are quite remarkable. I mean, one can actually see the deceleration of the spacecraft as it ploughs through the material, and you can see, I think it's 6 or 8, isn't it, distinct jets of material that Cassini goes through, and there's a little jolt, if you like, each time the spacecraft ploughs through that.
And in
Quite
fact,
remarkable.
Patrick, it took quite some persuasion to get the Cassini project to take us as close as 50 kilometres away from the surface, because they were quite concerned that if we flew through this dense plume, it might cause the spacecraft to
But
spiral
aren't you
out
going
of
even
control.
closer? I think there's a plan to go...
What we're planning to do, though, is when we go even closer, we'll make sure the closest approach is not in the plume.
Dense plume, well, how dense compared with our atmosphere?
Ooh, about a tenth as dense as our atmosphere.
As much as that?
We think it changes over time. So there are times when there's a lot more water vapour coming out of the plume than there is on other occasions. And so it's time changing, it's time
And
variable.
there's also evidence, isn't there, that these plumes are laden with at least some organics, some you know,
Yes.
there's a degree of complexity. It's
Yes.
not just simple water
No, it's not.
and CO. And of course, if this can happen on a body as small as Enceladus, I mean, who knows what else is happening in some of the other smaller icy bodies.
In fact, we're quite interested in Dione
Exactly.
because there is an outgassing source on Dione. It's not as large as it is at Enceladus.
Dione was 700-something miles across. Quite a big thing.
And in fact, in the extended mission of Cassini, we plan at least 2 flybys of Dione, and hopefully that will allow us to resolve better what might be going on inside the interior.
So we've come up with lots of reasons to go back to Saturn.
And what about Rhea, the satellite Rhea, with a ring round a ring planet?
Yes, there appears to be a ring of dust, of solid material. It was seen because it sort of cast a shadow in the signature of charged particles in one of the Cassini instruments.
In fact, though, it's a very diffuse ring of dust because the imaging camera hasn't been able to see it yet.
A ringed satellite of a ringed planet.
That's right.
All right, John. Titan.
Well, you know, that's, of course, the object closest to my heart. One of the fears I had before Cassini-Huygens arrived is that actually it would turn out to be a dull, bland, boring place.
It certainly hasn't.
It certainly hasn't. I mean, look, what have we found? We've found hundreds of thousands of square kilometres of almost certainly methane lakes and seas. We found rivers, channels. We found icy hills, small mountain chains, possibly cryovolcanoes, features that look like dune fields. I mean, the diversity of surface features is wonderful. How they're all connected up is still to be understood. We've for sure found complex organic molecules. Just how complex, we're not entirely sure. I mean, it is in some ways, it's the most terrestrial-like object in our solar system in some respects.
What is the very latest news?
Well, I think some of the most exciting observations of Titan have been published in the last couple of months.
Yes.
And these relate to measurements from the radar instrument. Every time that Cassini flies by Titan, the radar takes an observation along a stripe. It's, I don't know, 1,000 kilometres long by 150 kilometres wide. And this has been going on for several years now. And the team have put together all of these observations, and they can pick out distinct features now which they recognise. I think there are 30 distinct features. And when they put all of these together, many of them which they've observed several times, they realised that many of these features were in the wrong place on subsequent observations. And what they inferred from that was that there was something funny about the rotation of Titan. It wasn't rotating at a constant rate. And the differences were really quite extreme. And they've come to the amazing conclusion that actually the surface of Titan, the icy crust, if you like, is floating on a water ocean underneath.
Liquid, must it be water?
Well, mostly water. It'll probably be water with dissolved ammonia and various other salts. But, you know, fundamentally, Titan is a ball of ice. So you know, Titan has got not only these wonderful surface features...
Why do we only see ethane and methane as on the surface then? Why
wouldn't we...
Well, those are probably products from the atmosphere. Okay. There is a cycle which is similar in some respects to the water cycle on Earth, where you have, you know, water transferring from the surface into the atmosphere and then falling as rain. On Titan, we've presumably got something similar with methane and ethane. But then below the surface, the water represents the bulk of Titan.
Could this effect be due to the fact that not something odd about Titan's rotation, but the crust slipping, so to speak, over the
Yes, absolutely right. I think that's what it is.
Rotation's constant, but it slips.
Yes, the bulk rotation of most of Titan below the surface is essentially constant, but it's this surface which is slipping, and I think it's actually, the idea is that it's interacting with the atmosphere, the massive atmosphere. Momentum is transferring as a seasonal effect, in fact, between the atmosphere and the crust, which is what the radar instrument sees.
Well, if Titan's big, it's bigger than Mercury, not quite so big as Jupiter's satellite Ganymede, about the same size as Callisto. But why is it, do you think, that Titan has this dense atmosphere and Ganymede and Callisto have none?
I mean, the jury is still out. I think there is no fundamental and obvious reason why we've got such a dichotomy. As you say, objects which are almost identical in size and yet so different. Was it a single, if you like, catastrophic event that occurred which made Titan the way it is and Ganymede not so? I mean, we really don't know.
But we're hoping that this new Saturn mission that is being planned will be able to let us resolve some of those issues, because the plan would be there will be a spacecraft that goes into orbit around Titan, but there will be a balloon that spends months in the atmosphere of Titan, and so we'll be able to travel to different parts of the atmosphere.
What altitude balloon will it be?
I think the plan is to be about 100 kilometres to start with above the surface, but then slowly over a period of time it will move closer and closer to the surface.
How long will this mission be active?
The Titan orbiter, we would like it to orbit for at least 2 years. The Titan balloon, I think the plan is for 3 or 4 months.
That might be limited, might it, by power?
Yes.
By onboard power, it would probably, you know, have to carry its own power source. But, you know, the idea of being able to do in situ measurements for literally months, and in different places is absolutely
and in some ways the only power that we will need is to power the instruments, because the plan is to get the balloon into the zonal winds, and so the actual winds themselves are going to carry the balloon.
And that should take something like, I think, a couple of weeks to do a circuit.
That's why they'd like 3 or 4 months, because then they can get 8 or 9 circuits.
Well, we talk about these are balloons. A balloon is a balloon is a balloon. They've been used on Venus, so why not Titan?
Well, absolutely. And of course, many people have forgotten that we've already deployed balloons. In fact, it was the Russians on the 2 Vega missions.
Yes, indeed.
That's right.
In the 1980s. They deployed balloons with moderate success on Venus. I think one of them survived for a couple of days.
It did.
And took very, very good observations. So, you know, it's not science fiction to talk about deploying some sort of aerial platform, a balloon, in Titan's atmosphere. And Titan, of course, is ideal in some respects, with this very dense atmosphere, the relatively low gravity, and the zonal winds which would drive the balloons. You know, so we'd naturally get a survey of at least a band around Titan.
It'll be focused around the equatorial region because that's where the zonal winds are.
Any more landers? A lander on Enceladus would be a great thing.
It would.
Let's talk about landers on Titan, because I think the present studies are looking at the possibility of having sort of mini landers which the balloon could deploy, could drop, if you like, on some of the most interesting areas. And I think there's even a study which is looking at the possibility of a submersible or some sort of vehicle which could be dropped into one of the seas or lakes.
The last time we talked about that, we thought maybe we'll postpone that until the follow-on mission.
I mean, one thing, you know, we're talking about the satellites. What about Jupiter itself and the great red spot and now the little red spot too?
Well, the plan is that there are 3 different spacecraft that are being talked about. The US will be responsible for the Europa orbiter. Yes. The Europeans will be responsible for a Jupiter planetary orbiter, which will then go into orbit around Ganymede. And the Japanese will be responsible for an orbiter that will spend most of its time in the magnetosphere, in the environment. And the Japanese spacecraft and the European spacecraft will have remote sensing instruments on board. So they'll spend a lot of time looking at the atmosphere of Jupiter and trying to understand it better.
But this complicated approach, if I can call it that, that would involve at least 2 launches.
Yes.
So that's
and you've got to try and time them.
Of risk.
Yes, but you've really got to try and time them well, because we want to make sure that all 3 spacecraft are there.
What about timescales? When will the decision be made? Jupiter first or Saturn first?
Well, there are joint studies taking place between the US and Europe at the moment. The initial choice between which will go first will be in November of this year. And then there'll be a year-long assessment study. And a decision will then be made as to whether one of the outer planets will be one of the L-class.
But I think what is very exciting this time, you know, compared with the way things were 20 years ago with Cassini-Huygens, is that the agencies, in particular ESA and NASA, are working together at such an early stage.
And when would you hope the earliest could be for a launch to either Jupiter or Saturn?
They're talking, what, 2016, 2018? That's the sort of time frame.
So sort of 10 years away.
Well, it seems a long time away, but if we're going to design instruments that can survive either the environment around Jupiter or be small enough to be put onto the balloon which goes to Titan, we have a lot of work on our hands.
Well, absolutely. In fact, you know, you and your colleagues and me and my colleagues, we are already starting in the lab, you know, very early development work. Right. And, you know, people probably don't realise the sort of timescales that we have to work on.
For me, it seems a very long time ahead. And I feel that when they go up, I won't be doing the sky at night, but I hope you will. So, are you excited about it?
Absolutely.
And you?
I just can't believe that we're talking about going back so soon. It's wonderful, and I really think it's going to happen on this.
And I really don't mind where we go. Either of the 2 will be absolutely great. They really will.
Michele, John, thank you very much.
Thank you.
Thank you.
For our news notes, I'm going to begin with the Sun. The new solar cycle has started, and we had a major flare. Seen by the spacecraft, Stereo and Soho. Also seen and photographed by Pete Lawrence in Chelsea. And here's his picture. So the Sun is definitely waking up. Also, there's news from Venus. Chris, welcome back. What from Venus?
Yes, well, the European Venus Express probe has been in orbit for some time now, and there are exciting new results about the composition of the atmosphere. For the first time, they've detected what's called the hydroxyl molecule, oxygen and hydrogen stuck together, but it's a very important molecule. On Earth, it cleans pollutants from the atmosphere. On Mars, it sterilises the surface, so bacteria might not be able to live there. And in Venus, it seems to have this relationship with ozone. So we're getting to grips with the top of Venus's atmosphere for the first time, understand its composition, then you can model the atmosphere, and we can use that to test our models of Earth.
Meanwhile, on Mars, the Reconnaissance Orbiter goes on and on. Been taking very good images of the North Pole.
And not just images, radar data as well. We talked about the North Pole earlier, because we talked about Phoenix landing
site.
But we know there's ice under the surface, whatever Phoenix finds, because of Mars reconnaissance orbiters and other spacecraft firing radar down and detecting reflections from underneath. The MRO results are surprising, though. the North Polar Cap, this mass of water and carbon monoxide ice, should be pressing down on the top of the planet.
Quite.
So you should see it buckle. We see that on Earth.
Could be dead.
No, it's much tougher than you'd otherwise expect. That means it's colder, and that means this ice must exist a lot further under the surface than we otherwise thought. People had speculated that maybe there could be a home for life on Mars today at the bottom of these icy layers where you might have liquid water. But if that's the case, they must be a lot further down.
You remember in the early Sky at Night programme, we were talking about Mars, and it was suggested then the polar cap were nothing more than a very thin layer of hoarfrost. We certainly learned since then.
They are, and it's wonderful to have Phoenix in situ on the surface, digging down, and I can't wait to see what results it produces.
Now, let's go right outside the solar system. This is really your province, Chris, but the coolest brown dwarf star, only about 350 degrees centigrade, which is very, very cool for a star.
Well, as you say, it's the coolest. It's almost down to planetary temperatures. It's discovered by the Canada-France-Hawaii telescope, the CFHT, in their infrared survey. And there it is. It's the coolest star yet known. And we're really filling in the gap between planets and stars.
How far away is it?
It's relatively nearby. It has to be, otherwise you wouldn't be able to see these. It's a very faint, dim, small star. But it'll be interesting to see as these surveys continue, both at CFHT and other telescopes, whether we end up with any gap at all between the smallest stars and the biggest planets.
I think there must be. Their formation's different after all.
Sure, but maybe they might even overlap in masses. We're beginning to probe these regions, and we'll have an answer soon.
There's certainly a basic difference there.
Sure.
Now, again, something much more violent, supernovae. Colossal outbursts, always luckily a long way away. But now we've found the youngest supernova remnant ever studied.
Well, the most recent in our galaxy, certainly. Our galaxy should see 2 to 3 of these events every century. But the last one we actually observed was back in 1604, just before the invention of the telescope. We know there have been others since because we see the remnants they leave behind.
One around 1680.
That's right, that's the remnant Cassiopeia A. But astronomers have now found a much more recent example. By looking in the X-ray and the radio towards the galactic centre, we've been able to see the remnant of a supernova that must have gone off about 150 years ago. How do we know it's 150 years? Well, if you look at the images taken roughly 20 years apart, you can actually see the expansion of the remnant. If you measure the speed, you can use that to work out the age of the remnant. So just 150 years ago, this must have been a star and then exploded in the end of its life.
Well, I wonder when we'll get the next supernova in our galaxy. But looking much further out, galaxies can collide. And we're seeing one there, the Antennae Galaxies. Now apparently much closer than we believed.
That's right. We used to think they were 65 million light years away, and the new figure is 45 million light years. Now, why is that important? Well, it's because this is our canonical major merger. It's the closest example of 2 large galaxies smashing into each other.
It'll happen to our galaxy eventually.
It will. We think we're going to hit Andromeda. So we need to understand what's going on to predict the future of our galaxy and to understand how we ended up with the galaxies that we've got. How you produce elliptical galaxies by smashing spirals together, for example. Now, the fact that the antennae are closer means that lots of things suddenly make sense. The rate of star formation gets changed and now fits with our models. The size of the star clusters that are produced in the collision are now normal rather than 1.5 times what we thought they should be. So this one result, moving the antennae just by 20 million light years, makes a huge difference to our understanding of mergers.
Makes a lot of sense too. Chris, thank you very much.
Pleasure.
Next month, we're going to concentrate upon the Phoenix probe upon Mars. Until then, good night.
From one expert to another, stay tuned for The Life of Mammals with David Attenborough.